Fluid Mechanics, Unit 3, Dimensional Analysis and Turbines. Dimensional analysis is a method of dimensions. It is a mathematical technique used in research work for design and for conducting model tests. It deals with the dimensions of the physical quantities involved in the phenomenon. All physical quantities are measured by comparison, which is made with respect to an arbitrary fixed value. For example, length L, mass m, and time t are three fixed dimensions which are of importance in fluid mechanics. If in any problem of fluid mechanics heat is involved, then temperature is also known as fixed dimension. These fixed dimensions are called as fundamental dimensions or fundamental quantity. A dimension is measured of a physical quantity without numerical values, while a unit is a way to assign a number to that dimension. For example, length is a dimension that is measured in units such as microns, feet, centimeters, meters, kilometers, etc. These are seven primary dimensions called as fundamental dimension or basic dimension. That is mass, length, time, temperature, electric current, amount of light, and amount of matter. All non-primary dimensions can be formed by some combination of the seven primary dimensions. For example, force has the same dimensions as mass times acceleration, that is Newton's second law. Thus, in terms of primary dimensions, dimensions of force equal to mass into length divided by time squared. So mass denoted by the m, letter capital M, length L divided by time square. Primary dimensions and their associated primary SI units, English unit. These are all the basic dimensions: mass, length, time, temperature, electric current, amount of light, amount of matter. Mass denoted by the letter M in unit kilogram. Length is denoted the symbol L, unit meter. Time is denoted by T and unit is second. Temperature denoted by T in unit Kelvin. Electric current denoted by the letter I, unit ampere A. Amount of light is denoted by the letter C, unit candela CD. Amount of matter N in the unit of mole. Surface tension as dimension of force per unit length. The dimensions of surface tension in terms of primary dimension is sigma is equal to force by length. Already we see force ml divided by t square and divided by length L. L, L cancel and mt square m divided by t square or mt minus 1. Next, dimensional homogeneity. Law of dimensional homogeneity. Every additive term in an equation must have the same dimension. Dimensional homogeneity means the dimensions of each term in an equation on both sides are equal. Thus, if the dimension of each term on both sides of an equation are the same, the equation is known as dimensionally homogeneous equation. The powers of fundamental dimensions, that is L, M, T, on both sides of the equation will be identical for a dimensionally homogeneous equation. Such equations are independent of the system of units. The change of total energy of the system del E is given by del E equal to del U plus del KE plus del PE, where E has three components, that is internal energy U, kinetic energy KE, and potential energy PE. These components can be written in terms of the system, mass, measurable quantities, and thermodynamic properties of each of the two states, such as speed, elevation, and specific internal energy, and the known gravitational acceleration constant. Okay. That is del U equal to m into U2 minus U1 and del KE equal to of m V2 squared minus V1 squared and del PE equal to mg Z2 minus Z1. It is straightforward to verify that the left side of the change in energy equation and all three additive terms on the right side have the same dimensions. Del E energy, that is energy equal to force into length. That's give del E m L square divided by T square. And del U equal to mass energy by mass. That is energy again. Then del U equal to m L square divided by T square. Then del KE, that is mass into kinetic energy, mass into L square divided by T square. That is del KE is also m L square divided by T square. Then del PE, pressure energy, mass into length divided by time square into length. That is del PE is also m L square divided by T square. In addition to dimensional homogeneity, calculations are valid only when the units are also homogeneous in each additive term. For example, units of energy in the above terms may be J or Newton meter or kilogram meter square per second square, all of which are equivalent. Suppose, however, that kj were used in the place of j for one of the terms. This term would be off by a factor of 1000 compared to the other terms. It is wise to write out all units when performing mathematical calculations in order to avoid such errors. Example, dimensional homogeneous for Bernoulli's equation. Probably the most well-known equation in the fluid mechanics is Bernoulli equation. One standard form of the Bernoulli equation for incompressible irrotational fluid flow is rho pressure energy plus kinetic energy plus potential energy equal to constant. Verify that each additive term in the Bernoulli equation has the same dimensions. Second, what are the dimensions of the constant C? Solution, pressure, pressure equal to force by area. So pressure, then force is divided into mass into length by acceleration. Acceleration is changed into mass length by time squared into area length squared. So 1 divided by length squared. Here mass m and here length square, here length. So cancel the length. Here length only having. So we write m divided by t squared, 1L cancel. Here we write only L. That is pressure energy. Next, kinetic energy of rho v squared. Then rho is density is denoted by mass by volume and v squared. Velocity length divided by time whole square. Velocity is denoted by length distance by time. So length by time. So square, here we put square. It's equal to mass into length square divided by Volume means length cube. So length L into L, length cube into time square. Here time square. So mass here length squared, here length cube. So cancel that length square, here only length. So now we write m divided by t square L. Next, potential energy rho g z. So rho again density, mass by volume, g acceleration, length divided by time square, z distance, length. That's equal to mass by length, length cube, volume. So length cube, length into length, length square, t square. So length square, length cube cancel. Here length only balance. So equal to m divided by t square L. Indeed, all three additive terms have the same dimensions. You see, these three all are in same dimensions. From the law of dimensional homogeneity, the constant must have the same dimensions as the other additive terms in the equation. Primary dimensions of the Bernoulli constant C equal to m divided by t square L. So hence we proved it. This is the dimensional homogeneity. So next example, non-dimensional equations. The law of dimensional homogeneity guarantees that every additive term in an equation has the same dimensions. It follows that if we divide each term in the equation by a collection of variables and constants whose product has those same dimensions as the equation is rendered non-dimensional. If in addition the non-dimensional terms in the equation are of order unity, the equation called normalized. Each term in a non-dimensional equation is dimensionless. In the process of non-dimensionalizing an equation of motion, non-dimensional parameters often appear, most of which are named after a notable scientist or engineer. For example, Reynolds number and the Froude number. This process is sometimes called inspectional analysis. As a simple example, consider the equation of motion describing the elevation z of an object falling by gravity through a vacuum. The initial location of the object is z and its initial velocity is w0 in the z direction. From high school physics, d squared z divided by dt squared equal to minus g. Dimensional variables are defined as dimensional quantities that change or vary in the problem. For the simple differential equation in equation 1, there are two dimensional variables, that is dimensional length and dimension of time. Non-dimensional or dimensionless variables are defined as quantities that change or vary in the problem but have no dimensions. An example is angle of rotation measured in degree or radians, which are dimensionless unit. Gravitational constant g, while dimensional, remains constant and is called a dimensional constant. Other dimensional constants are relevant to this particular problem or initial location z0 and initial vertical speed w0. While dimensional constant may change from problem to problem, they are fixed for a particular problem and are thus distinguished from dimensional variables. Non-dimensionalization of equation. We use the term parameters for the combined set of dimensional variables, non-dimensional variables, and dimensional constants in the problem. Equation 1 is easily solved by integrating twice and applying the initial conditions, the result is an expression for elevation Z at any time t. Z equal to Z0 plus WOT minus of GT squared. The constant of and the exponent equation 2 in equation 2 are dimensional result of the integration. Such constant are called pure constant. Other common examples of pure constant are phi and E. Non-dimensionalized equalization. Methods of dimensional equalization in two methods. One is Rayleigh's method, another one is Buckingham Pi theorem methods. Fraud number F4 equal to WO divided by root of GZO. Non-dimensional equation of motion d squared z divided by dt squared, that's equal to minus 1 by F4 squared. In dimensionless form, only one parameter remains, namely the Fraud number. Equation 6 is easily solved by integrating twice and applying the initial conditions. The result is an expression for dimensionless elevation Z as a function of dimensionless t. Non-dimensional result is Z equal to 1 plus t minus 1 divided by 2 F4 squared t squared. Non-dimensionalization of equations. There are two key advantages of non-dimensionalization. First, it increases our insight about the relationships between key parameters. Equation 5 reveals, for example, that doubling WO has the same effect as decreasing ZO by a factor of 4. Second, it reduces the number of parameters in the problem. For example, the original problem contains one dependent variable Z, one independent variable T, and three additional dimensional constants G, WO, and Z0. The non-dimensionalized problem contains one dependent parameter Z, one independent parameter T, and only one additional parameter, namely the dimensionless Fraud number. Fraud number of additional parameters has been reduced from 3 to 1. In most experiments, to save time and money, tests are performed on a geometrically scaled model rather than on the full-scale prototype. In such cases, care must be taken to properly scale the results. We introduce here a powerful technique called dimensional analysis. The three primary purposes of dimensional analysis are to generate non-dimensional parameters that help in the design of experiments and in the reporting of experimental results, to obtain scaling laws so that prototype performance can be predicted from model performance, to predict trends in the relationship between parameters. These are three necessary conditions for complete similarity between a model and a prototype. The first condition is geometric similarity, and second condition is kinematic similarity, and third is dynamic similarity. In next class, we see the detail about the dimensional analysis and their similarities.